For thousands of years, a creek in the Arizona desert was quietly doing something that rivers almost never do. It was building itself. Every single day, it laid down 10 to 13 tons of brand new limestone. It carved turquoise pools out of ancient rock. It fed an ecosystem so rich and so improbable that visitors who stumbled upon it assumed they had somehow crossed into the wrong continent. And it did all of this while pumping 20,000 gallons of spring water every minute through one of the driest landscapes in North America. Then, in 1909, engineers took almost all of that water away. For the next 96 years, one of the rarest ecosystems on Earth slowly stopped being itself. The pools shrank. The limestone stopped growing. The native fish retreated into fragments of what had once been their entire world. And when Arizona finally shut down the dam that had stolen the creek's flow, what happened next shocked the scientists who had devoted years to studying it. This is the story of a river that forgot itself and then
a gem. It is something like I've never seen in Arizona. I couldn't believe it when I first laid eyes on it.
Remembered. The river that wasn't supposed to exist. Arizona is built for endurance, not abundance. More than half the state receives less than 13 inches of rain in an average year. Rivers vanish into dry washes every summer. The Sonoran Desert does not accommodate extravagance, which is exactly why, when visitors descend into a remote canyon roughly 100 miles north of Phoenix and encounter brilliant turquoise pools cascading over gleaming white terraces, the experience registers as something close to hallucination. It looks less like central Arizona and more like Croatia's Plitvice lakes or the white mineral pools of Pamukkale in Turkey. But it is completely, verifiably real. The place is called Fossil Creek. It begins at Fossil Springs, where enormous limestone aquifers hidden beneath the Mogollon Rim, the dramatic escarpment that divides Arizona's high plateau from its desert lowlands, release approximately 20,000 gallons of crystal-clear water every single minute, maintaining a constant temperature between 70 and 72 degrees Fahrenheit throughout the year. That consistency is the key to everything. The flow barely changes between drought years and wet years, because the water feeding it isn't recent rainfall. Hydrogeologists believe the water emerging at Fossil Springs began its journey decades or even centuries ago, slowly percolating through fractured limestone deep underground. The Mogollon Rim acts as a massive natural sponge, absorbing precipitation over a vast area and releasing it through these springs at a rate so steady it borders on mechanical. But the water carries something else when it arrives. It is saturated with dissolved calcium carbonate, mineral content acquired during its long underground journey. When that mineral-laden water reaches the surface and tumbles over rocks and fallen logs, carbon dioxide escapes into the open air. As it does, the dissolved calcium carbonate can no longer stay in solution. It hardens. It coats whatever it touches. It builds. Scientists call this material travertine, a form of limestone deposited by flowing water rather than ancient seabeds. Most rivers spend their existence carving landscapes down. Fossil Creek does the opposite. It constructs terraces, natural dams, waterfalls, and the luminous blue-green pools that have become its signature. The coloration itself comes from light refracting through mineral-saturated water of exceptional clarity. The rock feeding this process carries a story going back further than most people can comfortably imagine. The limestone was originally deposited between 300 and 340 million years ago, during the Pennsylvanian period, when much of present-day Arizona lay submerged beneath a warm, shallow tropical sea. Every calcium ion moving through Fossil Creek began as the shell or skeleton of a marine organism that lived and died before the first dinosaurs evolved. Each new travertine terrace forming today is recycled material from an ocean that disappeared hundreds of millions of years before modern Arizona existed. This ancient geological inheritance also explains how the creek acquired its misleading name. Early explorers encountered branches, leaves, and stones encased in pale limestone, convincingly resembling petrified fossils. In reality, nothing had fossilized. The creek was coating fresh organic material in newly formed travertine so rapidly that it created a perfect illusion of petrification. A log that had fallen into the water weeks earlier could emerge encased in limestone, preserving every crack and texture of its bark. It was geology happening in human time. The constant flow of warm, mineral-rich water transformed this narrow canyon into one of Arizona's most extraordinary biological refuges. Surveys have documented more than 30 tree and shrub species along its banks, and more than 100 bird species moving through the corridor annually. Fish found nowhere else in the Colorado River basin outside this specific drainage evolved here over millennia. Amphibians depended on its year-round warm water. Black bears, mountain lions, and deer came because permanent water in the middle of the desert meant the difference between surviving and not. Long before Arizona became a state, Fossil Creek had been doing exactly what it does: building, growing, sustaining. Then the 20th century arrived, and everything changed. The creek that powered a city. By 1900, Arizona was being transformed almost entirely by copper. Mining towns like Jerome, clinging improbably to the steep flanks of Cleopatra Hill, had become some of the wealthiest communities in the American West after industrialist William A. Clark developed the region's vast copper deposits. Smelters ran day and night, and the new electrical machinery promising to replace steam power demanded one thing above all else: a reliable electricity supply. Phoenix was expanding. Jerome's operations were consuming staggering amounts of energy. Engineers and investors were searching the landscape for opportunities. A man named Lou Turner found one. In 1900, Turner filed a water claim on Fossil Creek. His thinking represented the dominant philosophy of the era: flowing water that disappeared into the desert without performing work was wasted potential. What Turner saw was hydroelectric power. Fossil Creek's consistent flow, combined with the canyon's dramatic elevation drop, nearly 1,600 feet, meant relatively modest engineering could produce significant electrical generation. Gravity would do most of the work. The challenge was immense. There was no road to the site. The nearest railroad lay more than 40 miles away, separated from Fossil Creek by mountains, cliffs, and unbroken desert terrain. Historical accounts describe more than 600 workers, approximately 400 mules, and over 150 wagons moving cement, steel, timber, turbines, and machinery across terrain that had never supported industrial traffic. Many of the laborers were Apache and Mojave workers whose knowledge of Arizona's geography proved invaluable. The work came at a brutal human cost. Extreme heat, primitive conditions, and steep grades claimed workers and pack animals before construction was complete. The total investment came to approximately $1.5 million, tens of millions in today's terms. On June 21, 1909, the Childs Power Plant entered service, named after S.W. Childs, a New York bond broker whose backing made it possible. Engineers used a 25-foot diversion dam to capture nearly the creek's entire flow before sending it through 8,800 feet of wooden flumes, then down penstocks that dropped the water hundreds of feet onto turbines below. Gravity, not storage, generated the power. The Irving Power Plant followed between 1915 and 1916, expanding the system further. The transformation was rapid. By 1920, the Childs and Irving stations were producing roughly 70% of Phoenix's electricity, a city whose population had nearly doubled in a decade. Streetlights, electric streetcars, mining equipment, and a growing urban center all ran on power from a remote desert canyon more than 100 miles away. The achievement was recognized in 1976 when the American Society of Mechanical Engineers designated the project a historic mechanical engineering landmark. Both plants joined the National Register of Historic Places in 1991. What went unrecognized for generations was the price being paid downstream. Every gallon redirected into those flumes was a gallon that never reached the travertine terraces. The turquoise pools slowly shrank. The limestone formations nearly stopped growing. Native fish retreated into increasingly small pockets of viable habitat, while invasive species established themselves in altered conditions below. The ecological accounting was running deeply negative, and nobody was keeping the books. When a power company voluntarily gave a river back. By the 1990s, the engineering marvel that had powered Phoenix's growth had quietly become a relic. Arizona now drew its electricity from massive coal-fired stations, natural gas plants, nuclear facilities, and high-voltage transmission networks stretching across the Southwest. The trickle of power still coming from Fossil Creek had become statistically invisible. What had once provided 70% of Phoenix's electricity now represented a fraction of what a major modern city required. The infrastructure had not aged well. Maintaining dams, wooden flumes, pipelines, and turbines built nearly a century earlier was becoming progressively expensive. And a larger challenge loomed: federal relicensing. Arizona Public Service, which now owned the system, would need to secure a new license from the Federal Energy Regulatory Commission, requiring extensive environmental studies, potential modernization, and millions in compliance costs. The numbers no longer made sense. At the same time, the scientific case for what the creek represented had been building steadily. Fossil Creek was one of the largest active travertine systems in the United States, a biological oasis hosting rare desert fish, intact riparian forest, and hundreds of wildlife species. Organizations including the Center for Biological Diversity, American Rivers, the U.S. Fish and Wildlife Service, the U.S. Forest Service, and the Arizona Game and Fish Department argued that diverting nearly the creek's entire flow made little ecological sense when the hydroelectric project had become economically marginal. In 1999, Arizona Public Service voluntarily agreed to decommission the Childs-Irving project and restore Fossil Creek's natural flow. No court ordered it, no federal agency had condemned the facilities. A PS concluded on its own that restoring the river offered greater long-term value than preserving infrastructure whose best days were behind it. In the American Southwest, where water rights are governed by the doctrine of prior appropriation, the principle that whoever first put water to beneficial use holds the senior right to it, voluntarily relinquishing an established diversion was almost without precedent. The decision carried a substantial price tag: decommissioning, removing portions of the diversion infrastructure, restoring the stream channel, and preparing the ecosystem for recovered flow ultimately cost approximately $13 million. Critics questioned whether spending that much made sense for obscure native fish with no commercial value. Supporters responded that what was being protected wasn't a fish list. It was a geological and biological system found almost nowhere else on Earth. For the Yavapai Apache Nation, whose ancestral homeland had included this canyon long before any engineer arrived, the decision carried meaning that economics couldn't capture. A painful irony ran through the moment. Many Yavapai and Apache men had been among the laborers who built the original diversion in 1908 and 1909. The dam that had altered their ancestral landscape for nearly a century had been constructed partly by members of the community whose land it occupied. At the shutdown ceremony, tribal historian and councilman Vincent Randall acknowledged that complicated history, his people had been proud to help build the dam because it represented opportunity in its time. But time had changed what was right. He offered a prayer asking the creek for forgiveness. Restoring the water, however, would not automatically restore the ecosystem. 96 years of altered flow had fundamentally changed the creek. The challenge ahead was unlike anything previously attempted. Scientists bet against 100 years of damage. The years between APS's 1999 commitment and the actual restoration gave scientists something they almost never have before a major ecological intervention: time to prepare. Most dam removal projects proceed reactively. The structure comes down, and researchers scramble to document what changes. Fossil Creek offered advance warning. Ecologists used that window to build the most detailed pre-restoration scientific baseline any comparable project had produced. Leading the effort was Dr. Jane C. Marks, a stream ecologist at Northern Arizona University whose research focused on how rivers function as integrated systems. Marks recognized immediately that Fossil Creek wasn't just a restoration opportunity. It was a scientific experiment on a scale that would never be deliberately designed, a full before and after study of what happens when an ecosystem's fundamental process is returned after nearly a century of interruption. Her team measured everything: water chemistry at dozens of points, nutrient cycling rates, photosynthesis levels in aquatic plant communities, aquatic insect populations, the mayflies, caddisflies, and stoneflies that form the foundational layer of a healthy stream food web, fish populations in both the degraded downstream sections and the healthy upstream reaches above the diversion, which served as the ecological control group, a picture of what the lower creek should have looked like all along. What those upstream reaches showed was both a reference point and a rebuke. Above the dam, the creek functioned as a fully intact travertine system with dense native fish populations and rich aquatic insect communities. A few hundred yards below, the same springs produced a diminished ghost of what they were capable of. Before restoration could begin, there was a biological problem threatening to turn the project into an expensive failure. 96 years of altered habitat had allowed invasive fish, largemouth bass, green sunfish, and other introduced predators to establish themselves downstream. Simply returning full flow without addressing them would expand habitat for invaders, potentially overwhelming native fish before they could recover. In the fall of 2004, nearly 100 biologists, fisheries specialists, students, volunteers, and agency personnel conducted one of Arizona's largest coordinated native fish recovery operations. Teams systematically removed non-native fish from the restoration reach, while simultaneously constructing a permanent barrier to prevent their return. On June 18, 2005, Arizona Public Service shut off the flow entering the hydroelectric flume for the last time. There was no explosion, no dramatic surge through the canyon. The springs simply resumed doing what they had done for millennia. Water spilled quietly over the diversion structure and began filling channels that had been reduced to trickles or dry gravel for nearly a century. Pools slowly deepened. Dry stream banks darkened with returning moisture. Scientists, managers, tribal representatives, and local residents gathered to witness the moment. They were cautiously hopeful. Damaged ecosystems typically recover slowly, often taking decades to stabilize. Most expected Fossil Creek to follow the same gradual path. What happened instead rewrote what the science thought it knew. What the desert river did next shocked even the scientists. The first surprises were invisible. Dr. Marks and her colleagues had spent years measuring Fossil Creek's metabolic function, the rate of photosynthesis, nutrient processing efficiency, the activity of microbial and algal communities at the base of the food web. When they analyzed the first post-restoration results, they found something that contradicted the standard model of ecosystem recovery. The creek wasn't behaving like a damaged system struggling back toward health. It was behaving like a system that had simply been switched back on. Photosynthesis rates increased rapidly in the weeks following restoration. Nutrient cycling rebounded toward levels measured in the healthy upstream reaches. The fundamental biochemistry of a functioning river restarted with a speed that stunned researchers expecting years of gradual recovery. Marks described the central lesson in terms now quoted throughout ecological literature. Water, she concluded, was the master variable. Restore it, and the ecosystem's most important processes restore themselves. Then came geology. Within weeks, researchers observed the ancient travertine machinery restart. New limestone began coating rocks, fallen branches, and stream beds along the restored reach. Over the following years, scientists documented entirely new limestone dams forming along roughly 6 miles of previously deprived channel, some structures growing more than 2 centimeters per year. They were watching a waterfall build itself in real time. The fish responded with numbers that seemed almost impossible to believe. The Sonora sucker increased by approximately 17 times. Desert suckers expanded by roughly 52-fold. The round-tailed chub, which had nearly vanished from much of its Arizona range, rebounded by around 70 times. And then there was the speckled dace, a small native minnow reduced to near local extinction in the degraded creek. Within a few years, its population had increased by approximately 150-fold, roughly 15,000%. Species on the edge of disappearing suddenly became among the most abundant fish in the canyon. The recovery moved in precisely the sequence ecological theory predicted but rarely gets to observe. Microbial communities and algae recovered first, rebuilding the photosynthetic base. Aquatic insects followed, mayflies, caddisflies, dragonflies, restoring the middle food web layer. Fish expanded as prey rebounded. Then larger predators arrived, reptiles, wading birds, mammals. Ecologists call this bottom-up recovery. Fossil Creek produced a textbook demonstration at a speed the literature had not anticipated. The broader wildlife recovery confirmed the pattern. Surveys now document nearly 200 vertebrate species using the canyon. The endangered southwestern willow flycatcher returned to recovering cottonwood and willow habitat. The common black hawk came back to hunt fish and frogs along restored stream corridors. Black bears visited during Arizona's hottest summers. The Sonoran mud turtle re-established populations along the restored reach. Perhaps the greatest achievement wasn't the return of any single species, but the exclusion of others. Thanks to the 2004 removal effort and permanent fish barrier, Fossil Creek eventually became Arizona's longest stream reach, containing a native fish community entirely free of non-native species, a distinction almost unheard of anywhere in the American West, where introduced bass, trout, and sunfish now dominate rivers that evolved without them. The scientific implications reached far beyond Arizona. For decades, restoration ecology had assumed heavily altered ecosystems required generations to recover. Fossil Creek challenged that assumption with hard data collected before, during, and after restoration, demonstrating not just that recovery occurred, but precisely how fast and in what sequence. Around the world, ecologists now cite it as one of the clearest demonstrations that restoring an ecosystem's most fundamental process can produce recovery speeds that surprise even the professionals who study it. The river won. Now, humans are the biggest threat again. On March 30th, 2009, just 4 years after the water returned, the Omnibus Public Land Management Act designated 16.8 miles of Fossil Creek as part of the National Wild and Scenic Rivers System. The designation recognized the creek's geological, ecological, scenic, recreational, and cultural values, and legally protected it from future dams and major development, making it only Arizona's second wild and scenic river, joining the Verde River. The irony is that this recognition immediately created the next threat. Before the restoration, reaching Fossil Creek required navigating long miles of rough forest roads. Very few people made the journey. Then the photographs started circulating. Travel writers, outdoor magazines, and social media discovered the turquoise pools. Thousands of visitors arrived, then tens of thousands. Parking areas filled to capacity. People waded into travertine formations, camped illegally, lit fires in restricted zones, and created informal trails throughout the recovering ecosystem. Fragile riparian vegetation, rebuilding for only a few years, was repeatedly trampled. Stream banks eroded under thousands of footsteps. Litter accumulated in places untouched since the diversion was removed. Dr. Marks described the situation with a sentence that has become inseparable from Fossil Creek's story. "We have this fear that we are going to love it to death." It wasn't an exaggeration. The ecosystem had recovered because it was given space to function naturally. Uncontrolled recreation threatened to disrupt those same processes through a different mechanism than a diversion dam.